We heard good things, a lot of good things about Wi-Fi. We have been hearing like what we should do in India. And we also heard about Wi-Fi 7, Wi-Fi 8, amazing numbers. End of the day, what we all need is we have to play our Instagram video and we have to do a live stream or live video stream to our family, friends, or girlfriends, right? So here I am going to talk about live streaming over Wi-Fi. I'm not going to give you too much technical details about Wi-Fi. I might be disappointing you in that way, but I'll be just going over some of the streaming concepts which I learned, and I want to share you that might help. So if you look at total internet traffic, almost 80% of internet traffic is today video streaming. Okay? If you look closely on the video streaming part, there are two parts of it. Like one is live streaming and another is on-demand streaming. On-demand streaming is nothing but you saw a video and you want to watch a video and you clicked on it and streaming starts happening. But when it comes to live streaming, you want to make a video call or like a Zoom conference call. Those are live streaming, right? Has to happen live. Another important aspect of live streaming is it's very time sensitive, right? So when I say time sensitive, if you're watching a sport event, you cannot miss important scenes. And today the basic connectivity backbone is Wi-Fi, and Wi-Fi has these mood fluctuations. Sometimes it's good, sometimes it's bad. If it's good, it's very good. And if it's bad, it's too bad, and we all know about it. We have been discussing that. Now I'm from Ring, part of Amazon, and our obsession is to keep neighborhood safe. And for that, we have our security cameras and doorbells, and of course on Wi-Fi. And since our obsession is to keep neighborhood safe, not just us, so we have to be very reliable. So it's a big, beautiful, complicated challenge. Now, just before, like 2-3 years back, before joining Ring, I had a local brand, I don't want to name, local brand security camera at my home, and someone came to my house to take my shoes, which was gifted by my wife. Okay, I'll show you that footage. Just watch closely. You have to wait for the last slide. Hey, what you have noticed is, I don't know whether you have noticed, he got a phone call. He was about to take the helmet off, there was a video stuck, exactly at the same point. And because of that, I could not catch him. My shoes was gone, but I caught him later. Okay, I will show you that at the last. But what would have happened, right? So I had a security camera at my home, I have kept it, and from my side, all I have done is just to save some cost, I bought a local brand camera and a router. That I learned a lesson, but anyway, like I lost my shoes, right? And especially that it was gifted by my wife, you know, right? Like what would happen, right? So anyway, so let us look at, like this problem statement is very clear for us. Now we are going to look through this problem and what would have probably happened, right? So let us look at like common deployment, very basic home deployment scenario, and see, like understand what difficulty like security camera companies face. Now if you look at a basic home, your router is there, and in basic home, like see gadgets, right? These IoT gadgets are naturally placed in such a way that they have a signal relationship with the router. So your TV or your VR will be more closer to your router. It has strong signals. And your laptop or your mobile, you may be probably sitting in your bedroom and you have some like medium range signal. but your security cameras, your video doorbells are little away from your home router, and obviously obstacles will be there in between, which all puts them in that fair signal strength range of -65 to -75 dBm range. So it's heavy lifting. And at that range, this devices has this natural affinity towards sticking on the 2.4 because the range is a little more, and these guys will stick on to 2.4 more usually. And you also have to remember that we know 2.4 gigahertz, right? What problem it can bring in terms of congestion. There is another catch also we face, that these security cameras like has these advanced features like motion detection, and if somebody passes by, one guy detects motion and starts streaming, and then he passes and ring the ding bell, then that guy also starts streaming. So it's too much of bandwidth consumption happening at the same time on 2.4 gigahertz. Now, let us understand a little bit philosophy of security camera product, right? Or what customers expect. Customers' expectations never go down, just like your manager's expectation on us, right? So if you look at camera philosophy, camera wants to kind of simulate the same kind of things what a security guard can actually do. So it has to kind of catch that best quality video, and it has to also detect motion, and it has to, from the motion detection video, it has to identify it's a person, vehicle, or animal, and also intimate the user that, hey, there is an animal coming in your house, or there is a person coming to your house. And also, if there is any situation, we should have the ability to alarm, to put siren, right? Customers' expectation is too much, right? And we have been delivering that, and that shows how good we are in terms of meeting the customer's expectation. Now, with all that, basically what we'll go into it is, right now that we have discussed about the problems which we face in terms of deployment, let us dive deep a little bit about understand the problem from the streaming angle, from a video camera. So it's I'll be taking some of the concepts of streaming, so bear with me for some time. So streaming generally is from one end, you will be passing the information to the other end, and you have to see it live. And so we will be looking closely on this aspect to explain the problem, what we have just seen. Yeah, what is actually a video? A video is actually a sequence of images playing together, and when you play it in sequence, the brain perceives it as a motion, right? So which is basically a group of images or a group of frames or a group of pictures, right? So, and in effect, small group of pictures are being passed from one end to other end. Now let us look at this very closely, quickly. So how does light converts into frames, right? So light falls onto the camera, and there is a CMOS sensor which has the pixels in it, and the more the number of pixels, you call it as 2K, 4K, and this pixel basically carries the more information about the image which has captured. More the information, more clarity you will be able to see from the image. And this data is being converted to analog to digital conversion, and that data will be called out as bare data, which will be in an RGB pattern. And then this will be given to image signal processor. Here it removes all this information of noise reduction, removes some coloring. Finally, it makes it look like an image which is of more information in it, still more information in it, but it is look like a proper kind of image in a format called YUV. This is uncompressed. It has huge data per image, and then it will be given to encoder. Encoder is the big guy in the family, and we should know what he do. So he basically compresses it. One part of the function is to compress the bit stream, because your YUV uncompressed data cannot be put over internet. We have been telling about the Wi-Fi problems and all. You cannot just put bigger chunk of data directly to internet. You will lose packets and you cannot get that experience, right? So it has, encoder plays an important role in compressing the data what has been received from the ISP. Now let us look at what encoder actually do. This is very important. I need your attention for 2 minutes. So what is coming into the encoder is the YUV formatted, which has more brightness and more color, and it has huge data, right? Group of images. What encoder does is, encoder looks at those images and see the commonality of it. if there is a commonality of that, if there are common things happening on those images, it makes one image or one frame which has all the common things of that 24 frames. That we call it as intra frame or iframe. And then only the change of the pixels on those images only will be taken, and that will be formed as P frame or predictive frame. For example, like if I am walking like this and all the background remains the same, the only change what is happening is me moving from one place to another place. So when it goes through the encoder, what encoder does is encoder makes the reference frame or the key frame or the iframe as whole picture, and in the P frames, the predictive frames, only my movement only gets captured. So in that way, how does it help is the amount of data which we are actually sending out has considerably reduced. And decoder can understand and make out the video from these intra frames and the P frames or the predictive frames. So when decoder gets these predictive frames, by referring to the intra frames and the previous P frame, he can construct the image and he can play it in a sequence. And that way, we don't end up pushing a lot of data into the network. Now you can actually see that from this image also, like the sun rising, and you are actually putting the movement or changing the movements only in the P frame. So iframes are the most important frame in a video sequence. Yeah, like as we just now discussed, more data gets converted into lesser data. Now, if you look at scene complexities, right? So you see like camera capturing. So some motions are happening continuously, like people are moving around and some car is moving. In such situations, you cannot have commonality between two frames. You have to, the encoder has to work hard. And you end up having iframe size and the P frame size almost matching when the scene complexity is more. And in a less static scene or less complex scene, you will have lesser data on P frames. And on static scene, you will have much lesser data. Now, when the network conditions is varying, let's say, so when network condition is varying, encoder gets the information that, hey, your network is a little shaky. You cannot actually send that much amount of information. You have to now remove some of the elements and try to reduce the quality of the image, and somehow but the video has to go through. So in that case, like it still tries to optimize by reducing the bit rate, but still like it will try to deliver what you want to see. That's why you see like when sometimes network goes down, you see the resolution changing, you see some blurredness coming and all, because there are a lot of hard work when Wi-Fi is like showing this kind of mood swings. A lot of hard work going in the back end from the encoder side to kind of stabilize the experience for the end user. Now let us look a little bit into the encoder. There are two layers for it. One is video coding layer and another is network abstraction layer. And in the video coding layer, there are these codecs called H264, H265. Innovations are happening over there to see like how much we can actually compress without taking away the quality from user's perspective, right? So it's there, that is H264 and H265. And from application layer, we get this information that, hey, your network is not so good. Packets are getting dropped. Now, like target bit rate, you have to set is maybe 1 Mbps. And I want to send 2K, which remains around 3 to 4 Mbps. But now your target bit rate is only 1 Mbps. That information will be given to the rate control mechanism, and then rate control mechanism indicate to the video coding layer that, hey, set a quantization parameter high. This quantization parameter is nothing but how it compresses. If the quantization parameter is too high, then it compresses too much. If it compresses too much, the video quality degrades. So these are some of the three functions which actually does in the video coding layer. And final outcome from the video coding layer of encoder is iframes and P frames. And these iframes and P frames within the encoder itself, it goes to the network abstraction layer, and then it processes that packet and processes that information in such a way that it puts some data like for the decoder to decode, and we call it as network abstraction layer units called NAL units. Now, basically what encoder does? What encoder does is balancing the video quality and the network bandwidth. So that's how, because how good the encoder is, that much you can able to kind of balance to some level, right? So coming back to our problem. So from this, it's pretty clear that One thing I forgot to tell you is one iframe and his brother p frames. Then at sequence, we will send another iframe and its brother's p frames. So one iframe to the p frames up to the next iframe is called one GOP. We call this group of pictures. And like that, multiple GOPs forms one video sequence. So in my video or that video which you have just saw, it happened there are multiple GOPs has gone, and one of the iframe would have carried that guy's face, right? This is very evident that that iframe would have missed from in the network. So we need to understand what would have happened. Yes, so this is the whole point, right? So if iframe is missed and or some few p frames are missed, even if you received other p frames, that is of no use at all. You cannot construct that 2-second video in the other end. Now let us look at like what are the chances of losing this iframe when it traverses to the data link layer, right? So iframe has this null unit, and it converts it into null units basically within the encoder. Not only just iframe, all the frames from the encoder, iframes and p frames. We are taking the iframe because we just want to see like how many packets it gets converted from to how many packets get converted from iframe. So it has this null unit, means it has a payload, null payload, null header and null payload. So what it does is like decoder will know, oh, this is a video frame, this is how it has to be reconstructed. So that information is there in the null header and payload. And then it gets into RTP, like RTP will put like that sequence numbers, correct sequence numbers, and ordering for that. And RTP and RTCP, they work together to ensure some level of reliability, right? Like where RTP does is like it has this sequence number in the header, and in RTCP on the receiver end they send some report, RTCP receiver reports and sender reports. What they do is they show how many fractions has been lost, what is the number of packets, cumulative number of packets lost, and also some jitter information also will be there. From this, application can predict what is the target bit rate now I have to do. So there are a lot of packets missing. Accordingly, it sets the target bit rate and give that to the encoder. So this is some critical information which has been exchanged in the application layer and session layer. And from there, the packet gets its UDP. Typically, like UDP is being used in typical systems. And we get the UDP header on that. And then we get the IP header on that. And then when it goes to the it converts it to an MBDU, and then finally it goes to the MBDU, right? So basically we traverse from application layer and the session layer, RTP and RTCP, and then went to presentation layer, transport layer, network layer, and data link layer. Basically we just now covered all the layers where we just now discussed. So which means that, this is just a representation from the packet capture to show that all the headers from when it goes through different layers. So which means that if let's say a 250 KB of iframe have been traveling down, so it typically if you do a math, it converts it into around 171 packets almost, and which means like it converts it into around 4 to 5 MBDUs. One MBDU gets lost, one part of the iframe gets lost, then your entire iframe is gone. If your iframe information is gone, then your video sequence is completely gone, right? So that's what it has happened in my case. In my case, obviously the deployment was in such a way that it was a little away, and when I checked, there were 6 active devices was also there, TV and other smart devices. There is good chance that in such a condition, there is at least one packet can get lost, and it is very obvious that we need to have better reliable systems, better aggregation optimizations, and proper rate adaptation, enough retries. We need to have efficient beamforming system. Basically, we look forward to Wi-Fi 7, Wi-Fi 8, yes, very good. But today we have a lot of aggregation principles which is already there, which we are not effectively using it. We need to know how we can actually effectively use that. And also on the rate adaptation part, we need to be like very careful on that part. So after learning all this, so I understood that it's very important to have this iframe prioritization rightly, right? down the lane from DSCP prioritization to converting that to a WMM prioritization. All that's very important. So I try to kind of use our ring camera system to see like, hey, is there any change happening? And I got that guy, and I'm going to present him in front of you. And that's the missed iframe in the GOP. That's it. Thanks everyone.
Yes, we have time for questions. Please put up your hand. Mike, anybody, any questions for Vishnu?
Techniques.
So the only disadvantage or advantage over the Quick is we cannot encrypt like how we do RTP or RTCP frames. So everything is going to be encrypted payload or encrypted header itself. So you can't even differentiate an ACK packet and a data packet. So that's where the challenge could be coming forward, because the YouTube live is on Quick. The Netflix have migrated to Quick, for example. So identifying the RTCP kind of message is going to be much challenging. I think somewhere WMM prioritization or any Wi-Fi prioritization is going to be a much bigger challenge in that space.
Yeah, right.
We have one more question.
Yeah. Hi, Vishnu. So, given the importance of iframe over pframe, would you generally prioritize iframes down the stack with DSCP tags or WMM tagging over pframes?
Good question. We can do that, but I cannot just tell that like how we do it. But yes, prioritization possibilities are there where we can inform Wi-Fi driver that like, hey, just prioritize this iframe. But I have not seen, we won't see that more often, because more systems like users, like when I just checked out, most of them are like DSCPs are not prioritized.
I have a question while we get the mic to him. So what is the lesson from your exercise and experimentation? Is it like when you sell your ring, obviously you have optimized some technology inside, but obviously the router is bought by the people in the home, right? So do you then see a way for you to alert the user saying, hey, bring the router closer, or you'd run some tests and say, hey, upgrade your router? Is there anything that you think you can add on as guidance for the user so that all the innovation done on your camera side effectively, gives them the result that they are hoping for?
Yeah, so what we generally, yes, a good question actually. So what we generally do is like, we give some video during the time of setup, saying like, hey, you just check on the signal strength, and if it is there, consider a mesh network there, or consider moving it closer. So we can only do that, but still like we will get all the kind of issues where when you look at the metrics, most of the cameras are lying in this range, and there will be this problem, right? It may be a streaming problem or it may be a connectivity problem, and this exchange of information keeps happening, right? So yeah, we can educate and we can also optimize, but there is a limit for optimizing all these things.
So at this time, you don't have a solution where if there is a poor Wi-Fi problem due to a router being kept away, you can't do much except alerting the user.
Yeah, we can do a lot of bitrate adjustments whenever we see that there is a bitrate drop. So that layer in the streaming side, we can actually push that to a lower bitrate. But again, in certain scenes, like there is a fast moving and all, user will face that, right? So, or on the Wi-Fi side, I hardly see MBDUs being coming properly, like, or aggregation is being actually properly used. So from a Wi-Fi perspective, how fast you can actually send the data to the other end in the smaller slot, right? If you get a smaller slot, how fast you can actually send it. And if there is a missing, like how many times you retry that. So on that area, definitely I feel like we need to look more closely, and there are chances where we can optimize that area more. So we can actually we don't need to run into these many issues.
Last question before we break.
Yeah, hi. So you've spoken a bunch about video live streaming, right? So how important in your experience do you think is audio live streaming for devices, IoT devices like Ring, for example? And are we doing a bunch of innovation in that field as well?
Audio, in fact, when I say like when this video, audio is also there, right? I mean, audio packets are also being sent, but problems which are faced by audio are lesser in my experience, at least in our use cases, because audio packets does not take that much data, at least. Like on video, like you have a lot of data coming, right? And you have the demand of 2K, 4K and all. So audio interference problems, I have not faced. I may not be the right person to kind of answer that.
Okay. So thanks, Vishnu.
Thank you.
So thank you.